To solve this problem, we're going to follow several steps. The first step to approaching any problem is to draw a free body diagram or a force diagram for that object. So I'm going to use my dot here, and I'm going to draw the forces coming off of the object. So this is a man pushes a 20-kilogram box across a horizontal surface with a force of 50 newtons. So I know that the applied force that he's using here, so F applied, is 50 newtons. Now, the other forces acting on the object are gravity and the force of gravity, known as the weight, we can calculate by using the equation mass times the acceleration due to gravity. We discussed this in our types of forces note if you haven't watched that yet. So the force of gravity is going to be 20 kilograms, 20 kilograms times the acceleration due to gravity, which is 10 meters per second squared. So 20 times 10 gives us a force of gravity, or a weight, of 200 newtons. Now another force that we have is going to be the normal force. So remember that these forces should be balanced in our vertical direction as to create equilibrium. So Fn. It says the box travels at a constant speed, so therefore, as we have it drawn right now, if there was only the applied force in the horizontal direction, we know that the object would be accelerating to the right. However, this object moves at a constant speed, so I know that there is also a force of friction that is equal to the applied force. So I'm going to draw my vector so that it's equal to the applied force and label it as force of friction. Now, like I was saying, we have to look at the x and y directions, or the horizontal and vertical directions, separately. So what I'm going to do is list what are the forces acting in each direction by creating a table. So I'm going to have the force if it's in the x direction or if it's in the y direction. This just helps keep me organized as to which forces are acting in which direction. And I'm going to list my forces in the force column. So I have the applied force, the force of gravity. I also have the normal force and the force of friction. Okay, so now what I'm going to do is list the magnitude of the force, including the direction, whether it's in the x or y direction. So here I have the applied force is acting in the x direction. So 50 newtons in the x direction, nothing in the y. Force of gravity acts in the negative y direction, so nothing in the x, and negative y direction, 200 newtons. The normal force, it's not in the x direction. Now I don't know the value of the normal force, so I'm going to leave it as a variable. The normal force. And force of friction, the same idea. I know it acts in the negative x direction, and I don't know the value, so I'm going to label it as negative force of friction, and nothing in the y. Now we said that our equation for Newton's first law is that the net force acting on the object is 0. So the net force equals 0. So as long as the forces are balanced, the object will move at a constant speed. So as soon as you see those words constant speed, you know that the net force is 0. So what I'm going to do is add together everything in my x direction and set the sum equal to 0. We know that sigma means the sum. So the sum of my forces in the x direction, we'll start there. So down here. So the sum of the forces in the x direction are going to be the 50 newtons from the applied force minus the force of friction, and we set this sum equal to 0 according to Newton's first law. So I know 50 newtons minus the force of friction equals 0. So therefore, 50 newtons is my force of friction. We're going to do the same thing for the y direction. The sum of the forces in the y direction are going to be the negative 200 newtons from my force of gravity plus the normal force, and I know again this sum is equal to 0. So again, solving this equation, negative 200 newtons plus the normal force equals 200, I get that my normal force equals 200 newtons. So now I've solved for my force of gravity, 200 newtons, my applied force, my force of friction, and my normal force. So I've solved for all of the magnitudes of the forces acting on the block.